Okay, hi folks, Dr. Cole here. Let's move on to the next lecture. Let me go ahead and share my screen. Thank you very much. Okay, screen is shared. Let's go ahead and get to the lecture. Okay, very good. So we're going to do now correlation and linear regression part 1 with JASP. Okay, so while some statistics textbooks have correlation and linear regression in separate chapters, I think it's best to teach them together. You will use correlation when you want to know whether any two numeric variables are associated. With correlation, the result, the parameter is called R, tells us the strength of the association between all possible pairs of numeric variables in a data frame. R, which is the correlation coefficient, the values range from -1 to +1, where 1, regardless of whether it's negative or positive, refers to a perfect correlation, and 0 is no correlation. Now, R is essentially an effect size. So if R equals 0, that means there was no effect. The magnitude is 0, no correlation. If R is 0.1, regardless of whether there is significance in that R, and we'll talk about that in just a moment, it's considered a small correlation. If R is 0.3, it's a moderate correlation. And if R is 0.5 or more, it's a large correlation. There are basically two common correlation coefficients in business statistics and biostatistics. There's Pearson's correlation, there's Spearman's rho. We're using Pearson. It's really called the Pearson product moment correlation. It's the most common form of correlation. It is a parametric test, therefore it assumes that the data are linearly related and that the residuals are normally distributed. Remember, the residual is that difference between the mean and the score. Correlation is important to start the exploration of possible relationships you may want to investigate with hypothesis testing. Correlation results can be tested against the null hypothesis, and the null hypothesis in this case would be that R is 0, that there is no correlation. Sometimes a significant R might be a small correlation if the sample is very large. Now, just something briefly on correlation and causation. You have probably heard people warn you, correlation does not imply causation. This is a reminder that when you are sampling natural variation in two variables, there's also natural variation in a lot of possible confounding variables that could cause the association between A and B. So if you see a significant association between A and B, that is, if you see that the correlation is significant between A and B, it doesn't necessarily mean that variation in A causes variation in B. There may be some other variable, for example, variable C, that is affecting both of them. And this variable C is what we call the confounding variable. The word confound means to sort of disrupt. Okay. So whereas correlation will help you as the statistician with describing the strength of the relationship between two variables, a statistician will explicitly use linear regression or regression to specifically investigate the relationship between a dependent variable and an independent variable. So in other words, in correlation, we're not necessarily concerned that variable A is the independent variable and variable B is the dependent variable. In fact, we might not know really, or we may not care that we're interested in the relationship between independent variables and dependent variables, or between predictors and outcomes. We just want to start describing the relationships between pairs of variables. That's what correlation is for. But with linear regression, we can specifically say one variable is going to be y, the y variable, that's the outcome variable, that's the dependent variable, and one variable is going to be x, that's the independent variable or the predictor. Regression analysis yields a quantitative index of the strength of the association known as R squared or R squared. Regression analysis also yields an equation that can be used to predict unknown values, and we're going to practice all of that. We have simple linear regression, which is similar to when we did one-way ANOVA. So that's a hypothesis test of the relationship between a continuous dependent variable and one independent variable. And we can have multiple regression, which is similar to when we did two-way ANOVA, or ANOVA can be more than two-way. You could have a three-way, etc. So that's the hypothesis test of the relationship between a dependent variable and multiple independent variables. Now, what is different between regression and ANOVA? Well, in ANOVA, we need the independent variables to be factorial variables, that is, categorical variables. But in regression, we can use the continuous data. We can run regression with categorical independent variables, and we will practice a few examples. I put here R, that also meant JASP, R and JASP. And we will practice a few examples. So again, what I'm saying is what's unique about regression is that the independent variable can be both a categorical, it can be either a categorical variable or it can be a continuous variable. But what does linear regression do? Linear regression finds something that's called the line that best fits the data points. It's a line, it's linear. There are actually a number of different definitions of best fit, and therefore a number of different methods of linear regression that fit somewhat different lines. And with this best fit line, that's a linear regression. We could do nonlinear regression, but it's a little bit more complicated in JASP. We're not going to get to that in this course, but there is easily a way to do a nonlinear regression, and I'll briefly show you when we get to that. Okay, now regarding best fit, there are actually a number of different definitions of best fit, and therefore a number of different methods of linear regression that fit somewhat different lines. By far, the most common is ordinary least squares regression. So when somebody just says least squares regression or linear regression or regression, they typically mean ordinary least squares regression. In ordinary least squares regression, the best fit is defined as the line that minimizes the squared vertical differences between the data points and the line. For a data point with an x value of x1 and a y value of y1, the difference between y1 and what we call y hat 1, or the predicted value of y at x1, is calculated and then squared. And this squared deviate is calculated for each data point, and the sum of these squared deviates measured how well a line fits the data. The regression line is the one for which the sum of the squared deviates is smallest. An equation of the regression line is usually expressed as y equals a plus bx. The reason why we're saying B1 is because that's the first predictor. We may have multiple x's, x1 and x2. So A is referred to as the intercept. A is the y-intercept. So that's the value of y when there is no predictor, when x is 0. And then B, whether it's B1 or B2 or B3, that's the slope of the particular independent variable. And that slope, that B, is what we refer to as the regression coefficient, or they refer to it as the beta coefficient. So what is that in plain English? It's the change in Y for every unit increase in X. Right, so think of a graph, you got a Y and X, and every data point corresponds to a particular X value and a particular Y value, and that's where that data point exists. And so with all of the data, we can, statistics can generate a best fit line through all those data points. And once you know your y-intercept, which is A, and once you know your beta coefficient, you can use this equation to predict values of X for a given value, values of Y for a given value of X. For example, if our equation is Y equals 744.25 minus 0.2X, that's another way of saying that the y-intercept before we add any independent variable is 745.25. And then as we add the independent variable, as the independent variable increases by units of 1, the score goes down by -2. So we have a negative line, right? So something about X is bringing down Y. And that would be what we'd also call a negative correlation. So let's say if X was 600, then our estimated value of Y would be 624.25. Why? Because 745.25 minus 0.2 times 600 gives us 624.25. So let's get into some data and let's practice, and let's go ahead and do this in JASP. Here's our data frame. So go ahead and download it. And we're not going to do any manipulation in Google Sheets. So just go ahead and download this onto your hard drive, and then open up JASP. Let me make sure I've got this being downloaded to the save link as. Oh, wait, it's not quite right. I gotta open this up and then make sure we have that downloaded. And in fact, I'm clicking here to download, and I have already downloaded this, but we'll download it one more time just to make sure there's no mistakes. Okay, so we've downloaded it, and now we will come back to, where's our JASP? Open up JASP. Okay, there's JASP. Let's go ahead and open, go to our computer, browse to the downloads file, which is where I just downloaded this data frame. Here it is, LMAPI2. Let's go ahead and open it up. Okay. And let's take a quick look back at what these data are. So these are data from 400 elementary schools, randomly sampled from California for the year 2000. And our dependent variable, what we're looking at is academic performance or school performance. And the measure of academic performance is called API 2000, or here it is, it's API 00. What is API? That's like the academic performance index on a scale of 200 to 1000. So think of this as basically academic performance from test scores, statewide testing by the students in a school. It's elementary schools. And then we have a bunch of predictor variables. Growth. Well, it looks like growth is just the change in the score, so that wouldn't really be a predictor. Here's a predictor: meals, percent of students receiving free meals. L, number of students who are English language learners. Year round, whether the school is opened year round or not. I mean, year round, it basically means, do the kids need summer school or not? Mobility percent, first year in school. Class sizes, percent of parents who did not complete high school, percent of parents whose highest education is high school, percent of parents whose highest education is college, percent of parents whose highest education is college graduate, percentage of parents whose highest education is graduate school, and an average parent education, percent of teachers with a full teaching credential, percent of teachers with an emergency teaching credential, number of students enrolled in the school, percent of students receiving free meals. So it looks like that's going to be meals up here categorized already for us. And then percent of students with parent attended some college. So I guess that is this one, some college. Okay. That's our data. Come over to here. So basically, some of these should be continuous variables. Year round probably should be not, that's appropriate as a categorical, but mobility should be a continuous variable. That's a scale. What else? This is probably should be because that's the number of students. So some of these just didn't quite get imported correctly into JASP, and that happens every now and then, and it's important that we make them correct. Average education, that's a continuous variable. We would want that to be a scale. Remember, scale means continuous. I think everything else is right. Meal, cat, and call, that's either ordinal or nominal. Ordinal is fine because it is in order. As we go from 0 to 1 to 2, we're increasing in the number of kids that needs meals, and as we go from 0 to 1 and 2 with Colcat, we're increasing with the number of parents with some college education. Okay, so I think the data frame is good to go. All right, great. So we might as well save that now so we can not lose that. Okay, so we've saved it as JASP, and now we're ready to continue with our lecture. Let's start with exploring the relationship between student academic performance and characteristics of the school. Let's start with using variable APIOO. That's one we're going to use for demonstration and for the assignment. And that's academic performance. So that's going to be our outcome variable. And we want to see, how do we predict student performance by, let's start with number of students in the school. All right, so number of students in the school is enroll. Enroll is the number of students in the school. So before we even do any analysis, we can start to guess, we can make some hypotheses. We might hypothesize that better academic performance would be associated with lower number of students enrolled in the school. And so our null hypothesis would be that the correlation between APIOO and enroll is 0. And if we can reject that null hypothesis, then we can infer H1 that there is a significant association. And then we would want to actually look at the value of R and find out if it is it a what's the size of that R. So what do we do? How do we do that in JASP? We're going to select regression as the analysis bucket. And within that, there'll be correlation. We select our variables. The default is Pearson's R. We're going to ask for significant, flag, scatter plot, statistics, confidence intervals. Okay. So let's go to JASP and go to regression, correlation. And let's put API in there, and let's put enroll. All right, so whatever we put in here, what correlation is going to do, it's going to be looking at the correlation between all the possible pairs. And we're going to get into multiple correlation in the next lecture. So let's just keep it simple for now. We can see right away that the p-value is significantly below 0.05. So we clearly have a significant correlation, and that correlation of 3.18 is around the medium, right? It's around the medium to the large. we can do some things to help us. We can say flag significant correlation. So there's the 3 asterisk that's showing it. In fact, it's less than 0.001. You could do the confidence intervals. That's basically what I like to do. And then we can do a scatter plot. So that is showing us all of the, here's all the scores, and it's showing us the best fit linear line. So we've got, what do we have here? We have enroll is on the x-axis, and it put API on the y-axis. And we could add in, if we want, we could add in our densities so that we can see the distribution of those scores. And then we can also add statistics, so it will put into this figure the R. So this is a pretty cool, nice, cool figure, and we have our correlation. Now, one thing I do want to point out is if we go to descriptive statistics, we can do the same thing. We can bring in API and enroll, and then under statistics, excuse me, under plots, under customizable plots, we can ask for the scatter plot. And this is basically what we saw before. It doesn't show us what the correlation is, but it gives us the best fit linear line. Now, we don't have this phenomenon here, which is that the relationship is, let's see if we can switch these around. Does it change it? Let's put enroll first. Yeah. So there is something at the kind of the very end that might suggest there's what we might call a nonlinear relationship, but there's just a few scores where this is happening. Something in some of these school districts when there's a lot of kids that at the very end, it seems like the academic performance is coming back up. That could just be an anomaly. So generally, we've got here a linear relationship, right? Early on, the academic performance doesn't necessarily seem to be affected so much by the number of kids in the school. But as you get above 500, then we get this drop in academic performance. So I just wanted to point this out to you that you can have a best fit linear line. And by adding in the confidence interval, you can start to see how that spreads out and shows variability. And you may want to look at smooth, which starts to ask, is there a nonlinear relationship? And that's more of sort of advanced regression that I'm not going to be covering in this course, but I'm happy to teach that to you in a follow-up email if you'd like to send me an email. It's really not that complicated to do. We'll probably do that more. Actually, you know what? Let's talk about that in the next lecture when we do multiple regression, because you need to add 2 independent variables to do nonlinear regression to test if in fact a nonlinear line, a curvilinear line, is a better fit than a straight line. Okay. Make a note on that. Okay, 1 second here. And then just one more plot that's really very cool in JASP. It's called the flex plot, which is sort of another way that we can look at some possible curvilinear relationships. So let's specifically put API, academic performance, as the dependent variable, and enroll as the independent variable. And there we see what R is doing within JASP is it's fitting the best fit line, whether it be flat or curvilinear, and it's suggesting that this is a better fit than the straight line. But we can see then what is going on here. Really, what we're most interested in is the fact that a large portion of the independent variable is reducing. We're seeing a drop in academic performance somewhere around the 500 to 1200. When enrollment gets to that sweet spot above 500, then we see a drop in academic performance. And that's really what we would want to be modeling or understanding from our regression line and our correlation. We'll come back to this flex plot more next week. All right, so we've done that. So far, so good. And let's learn a little bit about what we've looked at so far. So overview of what we've done so far. So we generated the correlation coefficient, right? That's back up here in the correlation up top here. And we see our correlation is negative 0.318. And we saw the p-value of that correlation, and we found that it was significant. And then we looked at the size of R, and we also generated a scatter plot. This is the scatter plot here, all of the different points. And we saw that in JASP, we have a couple of different ways we can do the scatter plot. We can do it right here in correlation, but we can also generate a scatter plot in descriptive statistics, and we can ask for either the same linear line that's generated in the correlation scatter plot that we did up here. In fact, we could add that confidence interval. There you've got the, in the plot, we have the confidence interval. So there's that, that same confidence interval that we saw in the descriptive statistics scatter. It's showing it just a little bit differently. It's showing a dashed line here in the correlation, and it's showing us the actual confidence interval in our table, our correlation matrix. And then we see when we add that the plot here, when we say show the confidence interval, that shows it like this. It's more of a shaded region. So we saw that, we learned about that. That's the scatter plot. And then we saw the 95% confidence interval. So now let's get into the regression. So what we'll do now is we're still in the regression bucket of analyses, and now we select linear regression. And we have a continuous predictor because regression allows for both continuous and categorical predictors. So now we're specifically going to say, let's make the dependent variable academic performance. The predictor variable is enroll, and in regression, you'll see in a minute, that's called the window called covariate, because everything is contributing to the variance in the dependent variable, which is why it's called a covariate. Then when we generate the statistics, we want coefficients, we want our estimates, confidence intervals, tolerance, variance inflation factor. We want to display the model fit, look at the descriptives, and then plot it out. Okay, so let's do that, and then let's take a look at some of the statistics that are done. So let's come back up here to regression, linear regression. And now we're specifically saying API is going to be our outcome variable. Our covariates, this is where we add in our predictors. If it's a continuous variable, it goes here under covariates. You can see the symbol for continuous is the scale. We can add a predictor that's a factor. That's the categorical variable symbol, right, for the nominal variable. We'll practice that in a moment. Let's put enroll here now. And as far as we're going to leave this as enter, we're going to be adjusting this next week. In the next lecture, we're not going to touch the model. Statistics, we're going to say, give us the tolerance and the variance inflation factor. Give us some descriptive statistics. And then in the plots, give us the marginal effects plots. All right. So let's go through what we have here. Here's our linear regression. So we've got here a model summary. And in the case of model 0, that's no predictors being added. So there's no R square. Remember, R square is the effect size, or it's R square is exactly the correlation squared. So when we added in enroll, which we already knew had that correlation of 0.318, when it's squared, it's 0.1. So that's about 10% of the variance in API is explained by whatever is in model 1. In this case, model 1 just has one predictor, which is enroll. And we get something called the ANOVA. In this case, the ANOVA is just telling us overall, is the model a significant model? And the answer is yes. The p-value is less than 0.05. It's a significant model. And then the coefficients, that's specifically then telling us our beta. And this is where we get our regression equation. So we're looking at our model that includes our predictor or predictors. In this case, it's one predictor, and that's model 1, because we've said model 0 in this case there was no predictor added. So it's basically saying the mean, model 0 is basically the mean of API. And we see here in the descriptive statistics, the mean of the academic performance is 647.62, and that is what the y-intercept is in model 0. So as we add in our predictor, when the predictor is basically 0, which is the y-intercept when x equals 0, we have a predicted academic performance score of 744.25. And then as we increase enroll by one student, we drop down academic performance by basically negative 0.2. So this is reflected here in this marginal effects plot that is showing us that we predict, regardless of whether it's a nonlinear relationship, from a best fit line perspective using linear regression, we predict that APA drops accordingly to increasing number of students enrolling using this best fit line. And we can add some things to that line. For example, a confidence interval to show us sort of how does that change, and that spreading out is where we saw from that scatter plot that we did have some points that suggested perhaps API increases in a few of the strange outlier schools that had a lot of kids in it. Maybe those schools that had a lot of kids had a lot of staff, a lot of faculty, and the kids did well. All right, let's explain a bit more then of what I just talked you through. What we just looked at then is a simple linear regression, one independent variable. Next lecture will be multiple regression when we have multiple independent variables. And let's overview some of the statistics that we went through. We looked at R squared. R squared is the percent of the variation explained by the independent variables. R squared is also referred to as the coefficient of determination. It is R squared. It's the correlation squared. So what is R squared? It expresses the strength of the relationship between the X and Y variables. It is the proportion of the variation in the Y variable that is explained by the variation in the X variable. R squared exists from 0 to 1. It's not negative, right? If you have a negative correlation and you square it, it becomes a positive number. So that's why when you take R and square it, we get from 0 to 1. Now we've learned about this before when we did our ANOVA lectures, and we learned at eta, or eta squared, and we said that that was the effect sizes. Well, what is eta squared? Eta squared is part of the R family of effect sizes. It is an extension of R squared that can be used for more than 2 sets of observations, and it measures the proportion of the variation in Y that is associated with the membership of the different groups defined by X. Remember, ANOVA is about groups, is about taking a continuous independent variable and making it a categorical variable. We don't have to do that in linear regression. We can leave it as a continuous variable, so we can live right with the R squared as our effect size estimate. So whereas eta squared is the effect size for ANOVA, R squared is the effect size of the regression analysis. It is defined as the proportion of Y accounted for by the independent variables. Pretty much a little bit lower than what we just looked for correlation, but it's what we learned about before when we did eta squared. So if R squared is less than 0.1, it's a small effect size. If it's between 0.1 and 0.25, it's a medium effect size. If it's larger than 0.25, we have a large effect size. And again, it's about being able to say that an independent variable or a set of independent variables explains a certain percentage of the variation in the dependent variable. In the case here, what did we find? We found R squared is about 10%. So what is 10%? 10% is about a median. So we're able to explain about 10% of the variation in the academic performance by just considering the number of kids that are enrolled in the school. That alone explains a medium amount of the variation in academic performance. It's pretty good guesstimate then of what we might want to do. We might want to address school size, but we have other variables, so we would add more as well. We'd really want to take a look at the full set of independent variables that we have available to us to really understand the picture. But point being, it's pretty good. We looked at the model, and I said the model refers to adding predictors to investigate the Y variables. That's what you mean by model. So in the baseline model, or M0, or the null model, that's our null hypothesis. That's what we're testing M1 against. And in this case, because we just have a simple linear regression, MO, or the null hypothesis model, is no predictors. And then M1 is adding in the particular predictor that we're investigating. RMSE, which is shown in the model analysis, RMSE, that refers to something called the root mean square error, a measure of how well the model's predicted values match the actual observed value. It represents the average distance between the predicted values and the actual values. Lower RMSE values indicates a better fit. And we see here the RMSE goes down as we add in predictors. So it's a better model. And then the ANOVA tells us that in fact, M1 is significantly better than MO. So we can infer that something is changing, is having a significant effect on Y. That's what the ANOVA is doing. The coefficients, we've got this beta, we have this regression equation. A is the y-intercept value of y when x is 0. B is the slope of the independent variable. The number refers to the particular number of predictor variables. Next lecture, when we do multiple regression, we'll have B1, we'll have B2. We may have B1 times B2, etc. Now, just something about the coefficients. There are unstandardized coefficients and there are standardized coefficients. So far, what we've looked, what is being given to us is in the coefficients section. When we click on estimates, it gives us the unstandardized and it gives us the standardized. We don't have to do anything extra. It already gives it to us. What's the difference between these two? Well, you can kind of see for the standardized was 0.318. Where have we seen that? Well, that was the correlation between enroll and API. So correlation is in fact like a standardized statistic. It's already been standardized to Z distribution units. And the unstandardized then is the coefficient. It's the slope in the units of your predictor variable. So in fact, as enroll goes from, let's say, 500 to 501 students, the academic performance drops actually 0.199 the score drops by 0.199. And that's in the units of enroll. Now, if we standardize enroll, then it's going to drop by 0.318, which is really like standard deviation units. So as we drop one standard deviation in enroll, we drop us by a score of negative 0.318. And then when we compare multiple predictors, standardized becomes helpful because then we can just compare them next to each other as far as a standardized magnitude rather than the units of the dependent variable. And I've laid that out for you here. So the unstandardized coefficient is the original unit of the variable, but the standardized coefficient is standardized units, which is z-scores or standard deviations. Interpretation of the unstandardized represents the change in the dependent variable for a 1-unit change in the predictor. This represents the change in the dependent variable in standard deviations for a 1 standard deviation change in the predictor. The purpose of the unstandardized to predict values in the original scale, standardized coefficient to compare the relative strength of predictors. Comparison across predictors, not directly comparable if predictors are in different units, but when we do the standardized, it's directly comparable. So it's good to use them both, put them in your table, and I hope you can understand the difference between them. So in our example, what do we have here? Let's put these side by side so we can see what we have here so I can help us. Okay. We see here that API, right, because that's what we are predicting, equals 744.25 minus, why is it minus? Because the actual regression equation is y equals a plus b, but in this case, the b is negative, so we really don't say plus negative, we just say minus. It's 744.25 minus 0.2 enroll, which is another way of saying that we have a slope of negative 0.2. And what is that defined at? That's defined as academic performance index decreases by a score of 0.2 for each unit increase in enroll. Thus, if a school has 600 students, meaning X equals 600, right? So enroll equals 600, then we simply plug it into the equation, 744.25 minus 0.2 times 600. So we would predict, given linear regression, that if we had randomly selected from the data set a school that had 600 students enrolled, we would predict the academic performance would be 624.25. Okay. And in this example, enroll had a standardized beta of negative 0.32. And we would say, thus, a 1 standard deviation increase in enroll leads to a 0.32 standard deviation decrease in predicted academic performance. There are other elements of the coefficient table. There's T, and this should show you then that the way that the coefficient is being investigated as whether or not it's a significant slope or not. Think about it. If it's a straight line, there's no slope, so beta equals 0. But as the slope changes, how is it being tested? It's being tested using the t-distribution because it's a function of the sample size. What do we mean by the function of the sample size? Well, we have sample data. So it's controlling for the size of your data set when it's evaluating the significance of the slope, whether beta is significant or not. If the p-value is greater than 0.05, then we don't have a significant prediction. We don't have a significant change in y for every unit change in x. But here we have very, very low p-value. So yes, we have a significant change in y. That's the p-value. Something called tolerance and variance inflation factor. We look into that more when we have multiple predictors, but I'll define them now. The issue here is one of multicollinearity. So high tolerance is close to 1. And what we say is the predictor is not highly correlated with other predictors. And that's good. That indicates low or no multicollinearity. That's what we want. We don't want low tolerance, where the predictor is highly correlated with other predictors. If you have multiple X variables and they're all highly correlated, then they might be muddying up the prediction, and maybe it's best to just use one of them rather than many if they are highly correlated with each other. So we learn about that in the next unit. So in this case, we had, well, what did we have? Oh, it was a 1 because it's just one variable. So it's very high maximum tolerance. Same with variance inflation factor. And the phenomenon that we're looking for is something called multicollinearity. And I'm giving you a heads up for what we're going to do in the next lecture. But this is how much the variance of a coefficient is inflated due to the presence of other predictors that are highly correlated with each other. So a variance inflation factor of 1 means there is no correlation between the predictor and other predictors. So we have no multicollinearity. And when we look next week, as we get above 5, the VIF is above 5, we might have a problem. Okay. So far we have focused on regression analysis using continuous variables. However, it is possible to include categorical predictors in regression analysis. It just requires a little extra work in performing the analysis and extra work in properly interpreting the results. For example, in the data frame that we have a variable called year round. We also have another variable called meal cat. These are already categorical variables, and so we can use them as predictors, but we could also have created our own categorical variables because we practiced that when we did the ANOVA, where you could take a continuous variable and make a mean split or a median split or put it into 3 groups or 4 groups. So we already know how to do that. But we already have a variable year round, which takes the value 0 for the school that is not year round. I mean, they take a break from summer school. The kids don't need to be in summer school. They don't need to catch up. And 1 for a school that is year round, which means they stay open for summer school. And the variable meals is the percentage of students who are receiving state-sponsored free meals and can be used as an indicator of poverty. So I think meals was just that was already done for us. Let's just double check. Oops. Let's double check. That didn't need to be that big. Sorry. Drop that down. There we go. So if we were to let's go to descriptives, and let's take, all right, descriptive. Let's do another descriptive, and let's take meals and look at it by this meal cat. Let's see if we see 3 relatively equal groups. Yeah, not bad. Around 130, right? So it took our meals continuous variable, and they already made a categorical variable that's basically given us 3 equal group sizes of meal ranges. So it looks like, right, the lowest group is when you have a mean of around 20 meals. Oh, what is this again? This is the percentage. It's the percentage of students receiving free meals, right? So the higher the category, the more percentage. So category 0 is when we have on average about 20% of the students receive free meals. Category 1, about 65% receive free meals. And then category 2, about 90, almost all the students are receiving free meals. Okay, so we saw that. Let's keep learning. Okay. All right. So those are the two categorical variables. So now what happens when we include a factor as a predictor in a regression? So what ends up happening is the linear modeling function, that's what R does. What JASP is doing is JASP is built on R, and R to do regression in R, it's called the linear modeling function, LM for short. It is generating what's called a dummy variable, which is it's something that's happening internally for each category of the factor. So a dummy variable is a variable that takes values 0s and 1. And think about it like this. If we are in that particular category, then the dummy variable is 1. And if we are not in that category, the dummy variable is 0. It's a little bit abstract right now. It will make sense when we do the analysis. Let's start with, well, let's just explore for a second, see what happens if we try to do a correlation. All right, what if we say we want to do the correlation between API and year round? Okay, it does it, and when we plot it, here's the scatter, right? We have all of the API scores for when year round was 0, and we have all of the corresponding academic performance scores when year one was 1. And we see right here, what do we see? We've got a negative correlation. It is significant. It's pretty large, negative 0.47. So as this schools if schools are open year round, academic performance drops, right? Now, it will be good to know how can we predict that, and how much, what does the regression look like, so that we can learn how to do that. So we'll go now to linear regression. And now we have API as our dependent variable. If we try to put year round here, it will work, but it's not entirely the best place to put it, because it has a little asterisk. It's telling us it's not really a continuous variable. So instead, why don't you put it here under factor, and then it's going to tell you in parentheses what we're seeing. We are seeing then what the slope is when the value of our categorical variable is 1. What if we had mealcat that has 3 categories? We're going to see what the value is when it's a 1, what the value is when it's a 2. Why don't we see the values for when it's 0? Well, think about it. If it's 0, that's the intercept. It's turned off, because multiplying times 0 means 0. So there's actually no value of the predictor when it's a 0. So if we go back and we put in year round, the score, the academic performance when the school is 0, is open year round, that was year round equals 0, is 684.54. And then we would predict that that is going to decrease by minus 160 if the school is open year round. So the equation here would be y equals 684.53 minus 160. That would be how we predict it. Now, the neat thing is, since it's allowing us, or it's accommodating for factor, we could actually, instead of 0 and 1, we could put words there. We can just practice that now. So we can go to year round, and we can stay. The label for 0 is, are you open year round? No. Are you open year round? Yes. Right? So it could be no and yes. We could also just make it even easier. Not open. And, or really, what does not open means? It means no summer school. No summer school. And this one is summer school. Okay. Now we've changed it, the words. Summer school. Okay. And now then, when we look at the regression, see, it says what the labels are. So it just makes it a little bit easy to interpret when you have multiple categories, rather than having categories being labeled as 0, 1, or 1 or 2 or 3. Okay. In fact, so if we did the same thing, let's come back here to meal cat. And then if we say, what do we really mean? Well, if it was 0, that means low, right? Low percent of free meals. We can just do low, medium, and high percentage of free meals, right? Medium, high, right? A high percentage of free meals. That's what's going on here. And then when we put that in the regression analysis, then, oops, it's a factor. There we go. Then we can see. Now, how do we end up interpreting that? Well, I already showed you how we interpret this. If a school is not year round equals 0. The regression equation would simplify as API equals 684.54 times 160.51 times 0. So that is 0. So it's just the y-intercept. And then as we add in the year round equals 1, then we can account for the minus 160.51, because it's 160.51 times 1. So then API goes down to 524.03. Now, what about meal cat? Well, so let's come over here and take a look at this, what we see here. So group 0 is API equals 805.72. So that's when we have low meals, right? That was group 0. That was basically the dummy variable. The next category was the medium amount of meals needed, free meals. So now API goes down 805.72 minus 166.32. So it's 639.4. And then as we get high meals, it goes down to 504.38. And we can visualize that, of course. So we would just make sure that in our plot, marginal effects plot, maybe add in the confidence interval, and we can see what that plot looks like. And there we go. There's our marginal effects plot for how API is estimated to decrease. Now, there's not a whole lot of information here because the scatter is right around these categories. It would probably be better, since we have the information, no need to actually use the categorical predictor. We might as well use meals, because That's all of the scores. And then we see the line is basically what we saw from the three categories, but it's all of the information and not much variability, right? Very consistent, not a whole lot of fluctuation around that. And so we see here from the unstandardized coefficient, academic performance goes down by a score of 4 points for every additional percent of kids that needs a free meal. What's the R squared? Wow, huge. 80%. That's a huge predictor. We can predict 80% of academic performance just by the percentage of kids that need free meals. That's crazy. That's insane. And look at the p-value, it's so low. It's like times 10 to the minus 146. That's like incredibly significant. Very unlikely that we would make a mistake in our hypothesis testing. We can double check with this flex plot. Let's double check if is it really a straight line, or are there some moments when it might deviate into something a little bit more. Now look at that. A very almost a straight line predicting the drop in meals. So I actually really like this flex plot a lot, because the flex plot, and remember it's under descriptives, it's flex plot, it's going to show us that best fit line, whether or not that best fit line is linear or curvilinear. All right, what else do I need to teach you before I give you the assignment? I think that's it. All right, so recall that you could take any variable and turn it into a categorical variable for practice purposes, which I ask you to do in your assignment. So as an example, I'm reminding you how to take the college graduate, which is percentage of parents with some college graduate, and turn it into a categorical variable, right? We did that last week, but we can practice that again. Let's go to descriptive statistics and take college grad. Again, what does college grad mean? College grad means, I'm scrolling up to the top here. College grad is the percentage of parents whose highest education level is college graduate, right? And let's click on the statistics and say, give us 3 equal groups. So we see the splits here, right? 10, below 10, 10 to 26, and above 26, that'll create 3 equal groups. And I remind you how to do that R code. There, right, there's the 10, there's the 26, right? You'll create a new variable, and there would be your equation. Remember, we did that in the last lectures on the ANOVA. If you want, I'll demonstrate one more time. I'm going to take this and put this in memory. Copy. Come to our JASP file, edit data. Let's go ahead and add in a new column. We can put it here, that's fine. We're going to call this college grad category, right? 3, so we made 3 categories, and it's a nominal variable, and we're using the equation, compute with R code, paste that in, and now it did it, right? So now we've created a new variable. In fact, we could label it if we wanted to. So this is low, medium, high, tab through it and it'll populate. And then we could do the regression like we have done before. Maybe practice up in this one instead of, now we'll do college grad as a factor. Let's see, what did we get? About 37%, not bad. About 37% of the variation is predicted by whether or not your parents have a college graduate. And we can see here what happens. Score increases, right? There's our plot. Scores increase as the kids in school have parents with a college graduate, better academic performance. Okay. So this whole lecture, we did linear regression, and I showed you how to do the correlation. This particular plot that we did at first is what you would narrate the whole. This is really the ideal way to look at it, so we can see the distribution of our variables. Then we see the scatter plot. We see the best fit linear line. It's okay to also use that flex plot to be able to understand. We're just trying to understand data. That's our only job as statisticians, is understand data. Now, the thing that's different this week is, rather than saving this as an HTML and uploading it, I want you to present this. You need to narrate this. So how do you do that? Well, you got to go into your Canvas. You have to, let me see if I can demonstrate it here. Pretending I'm a student. All right, let's see. Go to your Canvas and log in. And I think you can basically pick any course. Any one of your courses should have Zoom. Any one of your courses has Zoom. Click on Zoom. And once you click on Zoom, that's your Zoom room. And you can go to your personal room, and you can start your room. And when you click start, it launches the meeting. Now, I don't know if this is going to do it, because I don't think you can launch a Zoom inside of a Zoom, but you would launch it, and then you will click on share your screen. And when you, well, before you click on share your screen, click on record, but you want to record is one of the functions. You want to record to your computer. Don't record to the cloud. Record to your computer. Make sure we see your, I need to turn on your video camera. We need to see you. Then you'll click share your screen. Then you can share your screen. Then you can walk through your output and narrate it very briefly. This week, for my assignment, I need to analyze API-00 and a predictor and tell us what you found, and then talk through the regression. And then when you're done, you will basically end the Zoom session. When the Zoom session ends, you will see the recording starts to render, and the recording saves on your computer. The recordings always go into a document section called Zoom. So you will see your recordings. Like, here's the one I did maybe last week. Yeah, so there's the recording. There'll be an audio recording, there'll be a video recording. The video is the video. It's what you just did. Then what do you do? Well, you're a Lawrence Tech student, and you have your Gmail account with Lawrence Tech. Well, with Lawrence Tech, your Gmail, you have YouTube. You have your own YouTube channel. So click on YouTube, and this is your channel. And then you can click on create. Another creation is, there's a plus sign right here, and you can upload the video. upload the video. When you click on upload the video, there's a few parameters you need to select. You need to select, here, I'll practice with you now. You need to select that it is, give it a name. You can say assignment, whatever, linear regression assignment 1. Then you scroll down. You need to say, no, it's not made for kids. Okay. Then you click next. And then click next one more time. Click next one more time. And then unlist it. It's not for the public. It's just to share with your instructor. And then there's the link. Copy the link. Click save. And that's what you will put in Canvas. That's what you're submitting. You're submitting a YouTube link this week. You're not submitting an HTML. All right. If you don't like it, you can cancel it. You can delete. Make sure I'm not screwing that up. All right. No, this one is good. Yeah, I didn't want to cancel that. So it's the one that I just finished uploading that I canceled. And your account will be your channel. So you can always change names and manipulate stuff and copy the links. Get the shareable link. That's what you share. If you have any questions, you let us know. This is it for this week. Okay. Thanks very much. Good luck. Bye-bye.